like...
Okay, so maybe how I'm thinking of explaining this is, first we're going to, I guess, go through what Fremont just explained here, which is like why we might want to compose additions and multiplications to construct something that stays private. And then I'm going to show you a very toy example of just like one addition and multiplication, and then explain like how you can keep that private. Okay, so the toy example here is like, Florent wants to show that someone's age in their passport is between 18 and 200. And so the thing he's drawing here is like, oh, like, in order to do that, it's one of the integers between 18 and 200. You're going to prove that like x minus 18 times x minus 19 all the way to x minus 200 is equal to 0. And that means as long as you have one of the values from 18 to 200, this whole thing will evaluate to 0. Okay, and so like concretely, like what this code, what you can represent this as like a sequence of additions, subtractions, and multiplications on top of this like unknown variable. And so the idea is we want to be able to prove that this statement is true without revealing x. Okay, so now we need like a 0 to 1 to prove. And what he's trying to describe here is like this AW.BW equals CW is like the like matrix that describes precisely what this constraint looks like. So let me give you like a more concrete example. Imagine we had like much simpler constraints, like A times B equals like C, and then like C plus D equals E. And like I'm going to make just E public, and then I'm going to say, look, by only making E public and maybe doing like a range check on D or something, I can prove to you I know some two values A times B, such that all of these A, B, C, and D, such that all of these are satisfied, but I only reveal to you E. And like, why is this interesting? Well, like this is like the prime factorization problem, and this is like hard. Like given some number, if the number is big enough, like 22,000 bits or more, it's like actually quite hard to figure out like the prime factorization of A times B. And then this is kind of an interesting statement because now I can say, hey, I know some value E, and maybe I can ask more constraints to show, oh, D is smaller than 18 or something the same way we did it here, like D is between 0 and 18, and some value between E and E minus 18 I know the prime factorization of. So in some contrived mechanism, like the single multiplication and single addition is still a somewhat interesting statement. Okay, and like in this scenario, you can imagine you can construct this like matrix, but I think this is like maybe like too much like complexity for just understanding like the most basic ZK proof. And so in practice, to do this thing, we do this whole process called draw 16, and then we like do a bunch of things, like proving key, verifying key, all this stuff. But that is like sort of complex and requires like a lot of background knowledge. But there's like a simpler protocol called ZKBoo, which is like similarly, it's like the performance is honestly like within an order of magnitude, and it's not actually used in practice anywhere because it was invented like 4 years afterwards. But I think it's like much more conceptually simple, so I'll try to explain that instead. Okay, so like concretely, like what is the like core thing we're relying on? And like feel free to like ask questions in the middle if you don't understand anything, because that'll also help. Okay, so like I'm gonna construct. So what we're going to do is we somehow like want some prover to convince like some verifier that they know these values. So what's going to happen is the prover is going to construct like for A, B, C, D, and E. So for each variable, they're going to construct like 3 shares. B1, B2, B3.
3 what?
3 shares. So like what it's going to be is like A, I'm just going to randomly divide into like 3 random numbers. B similarly, and like specifically like A1, A2, and A3 equal A, and so on all the way to the bottom. And so B, yeah. So okay. So let's start with like the most simple thing. Let's do just C, D, and E. So let's like ignore like A and B for now. So I'm gonna like put this line here. And what we're just going to do is prove this first statement of C plus D equals E, where I'm not going to reveal C and D. And so how exactly does this work? Well, okay, so like this is actually like mod P. Like mod P. Okay, mod P. And now the really nice thing of making this mod P is that
what is P here?
Just like some random known prime. Like everybody's agreed that some 256-bit prime, like really massive prime, is going to apply here. And so now, when I break up this C into C1, C2, C3, like, I'm going to do a process in which I, the verifier, query the prover about some of these random values. They don't reveal anything about the original values C, D, and E. And then the verifier only has a 1/3 chance, the prover only has a 1/3 chance of fooling the verifier. And then I do this process 100 times, such that at the end, there is a, I would have had to fool this verifier with a 1 in 3 chance 100 times, meaning that there's something closer to like 1 over 2 to 2d6, like a really good security guarantee that you get that the prover knows the values. Okay, so this is like the outline of what I'm going to explain, and then now I'm going to explain how we actually do this process. Okay, so first, how do we even get C1, C2, C3? So the idea is that we're going to choose a totally random C1 less than P, and a totally random C2 less than P. And then C3, we're just going to get from C minus C1 minus C2. And now, imagine you only know, C1, C2, and P. Without the other two values, C could literally be anything. And same with, if I know C2 and C3, but not C and C1, again, I know literally nothing about C because these two values are effectively random. Okay, and so, we're going to do the exact same thing for D as well. And so now we have, these, 3 kinds of, columns, and, this is, in crypto, we call this, NPC in the head, because these 3, imaginary people, 1, 2, and 3, are going to, do some computation, and we're going to, pretend we did it, but then only, basically simulate the, NPC process, but a much simpler version of it. Okay, so how exactly is this going to work? So what I'm going to do is, first I'm going to reveal, E, E1, E2, and E3, because this is the public output, and C and D are private. So I'm going to reveal all of these. Okay, and then, this is, step 1. And then step 2 is a verifier is, and I'm going to commit also to C, D, and E. So I'm going to output, in this case, I'm going to use a hash. In reality, we use a KZG commitment, but a hash is good enough for us. So I'm going to output, hash of C, C1, C2, C3, you don't even need C. For simplicity, C1, C2, C3, D1, D2, D3, and E1, E2, E3. Hash. Okay, so now I have these 3 values that have been output. And you can think of these as kind of now that I've output these 3 values, I've committed to them. I cannot change them anymore. Okay, now the verifier in step 2, so after outputting these values and these hashes, verifier 2 is going to choose 2 of the columns, and 1, 2, and 3 are random. So for instance, 2 might return 2, 3. And they're going to get this thing, they're going to get this via the Fiat-Shamir transformation, which is effectively they're going to hash all 3 of these values. So this is HC, HD, and HE, right? Hash of all the values of C, hash of all the values of D, hash of all the values of E. And 2 is going to do some process that looks something like H of HC, HD, HE. And they're going to take this value in ternary and take the last 2 digits, and they're going to get something like this. Effectively, they're going to use these values to seed random values 2 and 3. And I'll explain why this is important after, but it basically forces the order that you must have calculated these and then gotten the values 2 and 3. And I'll explain why this is important in a moment. But okay, let's say the verifier now chooses the random values 2 and 3. So now we're going to open columns 2 and 3. Now what opening means is this person 1 is going to reveal C2, C3, D2, D3, and already revealed E2 and E3. And so now what verifier is going to do is verify the computation is correct for players 2 and 3. So what does this mean? Okay, we know that if C plus D equals E, and we chose C1 and D1, so when I said we chose E1 and E2, so when I said we chose C1, C2, D1, D2 at random, and C3 and D3 followed, we can't actually do that for E1, because we want to verify this constraint C plus D equals E. So the way we calculate E1 is we say C1 plus D1 equals E1. The way we calculate E2 is C1 plus D2, C2 plus D2 equals E2, and E3 is C3 plus D3 equals E3. And this way, for each player 1, 2, and 3, C1 plus D1 equals C1 plus D1 equals E1 or whatever. And so now we just verify, so okay, so now step 3, I wish I started at the top now, but step 3 is you verify C2 plus D2 equals E2, and C3 plus D3 equals E3. Okay, and now And this is like some work that the verifier is actually doing. Or I guess you could say both of them are doing it because the prover kind of reveals and the verifier does the computation themselves. Okay, so now like what have we just done? Like the verifier chose 2 columns at random and verified those 2. Now imagine like the prover had tried to fool the verifier. They didn't actually know some C1, D1, or D1 that satisfied this. Then had I chosen 2 columns at random, I would have found their folly, right? Because imagine like C1 and D1 don't actually equal, C and D don't actually equal E, there's like some goof. Then like the best the prover can do is maybe fudge like C1 and D1 randomly make E1, C2 and D2 randomly make E2, then they're screwed over here because this equality cannot be true or else the whole thing would have been true. So one of these numbers must be wrong. Right? So maybe like, I don't know, they goofed like this number or something. Right? Now the chance of us catching this like goofed like say D1 is like basically like because we chose 2 out of 3 columns, we'll catch it 2/3 of the time.
But it's predefined what the columns are that are going to be selected. So if I know that ahead of time, can I just like make sure that my goof is in
Correct. So like why can the prover not just always put the goof in the unselected column? And this is what this hash commitment does. Is like this forces the order of 1 had to happen before 2. Because imagine if 2 happened before 1. Like first you chose columns 2 and 3. Like because we did this hash first, like first we hashed C1, C2, C3, D1, E2, D3, E1, E2, E3. Now they're stuck. You can't change these. You've emitted hash C, hash D, hash E. And like this brings us to the 4th step of we basically verify that these values came from this hash. So like step 4 is like we verify partially that like these hash values correspond to this original hash. And you can't actually do this with the traditional hashes, you know, like SHA-56, but you can do this with like this KZG commitment, which lets you like partially verify a hash. And so like one very like dumb way you can imagine, or I guess, is there like a dumb way to construct KZG? Not really. Okay, so just trust me when I say like that there is some hash function in which when I output like C2, D2, and E2, you can partially verify the hash. So basically like what I can do is once I output a C2 and D2, like I can partially compute this hash and say, okay, I'm gonna hash like just the C2, C3 part of this and verify it corresponds to that part of HC.
Yeah, but I still know that you're checking 2 and 3. So even if you can partially verify the hash, you can't verify that D1 in that hash is like a wrong number, right?
Okay, so actually, I think you can do this, and the way we're going to do this is instead of outputting the hash of all of them, we're going to output the hash of each one individually. So we're going to output like, we're going to output these, and we're also, I guess we're going to I'm going to like, what am I going to do here? I'm going to say like, we're going to output like, so like, okay, H equals hash. I'm going to say like H of C1, H of C2, H of C3, like H of D1, H of D2, H of D3, and then like H of E1, H of E2, H of E3. Okay, and so now like first the prover outputs these 9 numbers, then like the verifier like hashes all of them together, so like all 9 of these values together are going to get hashed, and then like these values are going to output, and then in step 4, I'm going to check C2, yep, that equals hash of C2, D2, yep, that equals hash of D2, C3, yep, that's equal, D3, yep, that's equal, E3, yep, that's equal.
Yeah, well, they're still, okay, but
right, and these are the unchecked values.
But I know you checking 2 and 3, right?
Yeah, but you know, like the problem is I calculated the values 2 and 3 based on hashing all of these commitments that you put together.
But can't I do that hash? Like, can't I do that computation and know exactly what it is that you're going to do? Or is that just too expensive?
Oh, I see. So you say like, you check that's what it's going to do,
Yeah.
And then if it is, then you're like, ah shit, they're going to catch me, let me redo it.
Yeah.
And then until you randomly kind of get it right.
Yeah. Or is that just too expensive?
Okay, so why can't you do this? Let me think. Okay, it's because you output all these values, and then you also output h of C, h of D, and h of E. And like when user 2 computes this hash, they're basically like you can imagine that like you wouldn't be able to fudge that if, for instance, E was public and I calculated these based on all of these combined. And like, okay, let me specifically like explain a little bit more. Like basically what I'm trying to do in my head is like simulate how we can reproduce the properties of like the KZG equipment we do with this like kind of hash approximation. And that property breaks. And so I guess I'm trying to think of how to reproduce that property in this analogy. And
Perhaps like if you just took like a random set of them to then do the compute, then they would need to have like done somehow all of the permutations to like ensure this. Would that make
like
sense?
I guess like I'm trying to combine the explanation of Fiat-Shamir to explain how you can make this non-interactive, but you can like for the sake of this explanation, you can imagine an interactive protocol in which the verifier literally just like chooses two numbers at random, right? Like because it's happened in this order, like let's say like it's not exactly a hash of all these values. Like you can imagine like this is maybe the random seed for the verifier secret randomness generating algorithm, and they generate random numbers 2 and 3.
Oh, okay.
And like that like secret random number generating algorithm, like you can make it so the prover doesn't know what it is.
Okay.
In reality, when you actually do this protocol and you want to make it non-interactive.
Okay.
But maybe it's easier just to do the interactive version first, where you pretend this verifier has like some random unknown random function. Okay, but it's a good question. So now if you have that unknown random function, now prover cannot predict which columns are going to be chosen, and so you're just stuck committing and like holding your fingers. Cool. Okay, so now do you believe me that for addition, there is a 1/3 chance that I can fool the verifier?
Yeah.
Okay, do you agree? Okay, cool. So now what I'm going to do is I'm going to expand this into multiplication. And I'm going to preview as a 1/3 chance you can fool the verifier. And then what it's going to mean is all together, like this whole computation of any sequence of addition and multiplication is a 1/3 chance you can fool the verifier. And then addition and multiplications are basically Turing complete. So I can construct any like mathematical function off of these. And specifically, you can construct this range check, you can construct any other nice function you want. And really interesting, you can construct both hash functions and signature verification functions. And so now you can do all of those secretly and hide the values you want to hide and reveal the values you want to reveal.
A, B, C, and D are all integers?
A, B, C, D, and E are all integers less than P.
Less than P.
Yeah. Yeah. So I should have explained because the addition doesn't actually matter if they're integers or not, but when we go to multiplication.
Yeah.
Okay, cool. Actually, everything was on mod P, so it does kind of matter that they're integers.
Yeah, fair.
Yeah, and the reason mod P is nice is then you don't have to worry if things overflow.
Oh, yeah.
Okay, things just overflow and it's fine, it'll loop back. Okay, cool. So how are we going to do multiplication? Well, like addition has a really nice property. When you break it down like this, C1 plus D1 still equals E1. But that's not true for multiplication, right? Like if I like decompose it into A1, A2, A3, and B1, B2, B3, it's like not the case anymore that like if A times B equals C, then A1 times B1 equals C1, right? And like that, what is like the actual equation here? It's like A1 plus A2 plus A3 times B1 plus B2 plus B3 is going to end up expanding into like each of the 9 cross terms. Right, so we're going to get this. We're going to get like AI, BI for like each value of I less than 30. Okay, so like maybe I'm gonna like write this out like A1 B1, A1 B2, A1 B3, A2 B1, A2 B2, A2. And then I put too much spacing between these. A3 B1, A3 B2. Okay, you get the idea. And then like what we're gonna do is instead of saying C equals like A1 plus B1, C is now going to be this other thing. And what C1 is going to be is we're going to take all the cross terms relevant to like C1 to make this add up. So like specifically, I think we're going to take each one is going to have 3 cross terms. So I think we're going to take A1 B1 plus A2 B1 plus B2 A1. And then we're going to take C2 equals A2 B2 plus 3 A3 B3 plus A3 B2 plus A2 B3, and this is plus A1 B3 plus A3 B1. Okay, so now if we add all these up, the multiplication lines up. Like what I've done is I've now said like, so remember how I said I chose C1 randomly? We're not choosing C1 randomly anymore. We're choosing A1 and B1 randomly, and C1, C2, C3 are going to be set according to this rule. And then D1, D2, D3 can be random again, or D1, D2 can be random again, and then E1 is going to be like C1 plus D1, C2 plus D2, etc.
So you're saying you only do this for C?
You only do this for C because of the multiplication.
Because okay.
Right?
Okay,
And so
sorry.
this means that if we set C1 to these values, now it lines up again. Now, there's one nuance here, which is like this now, like when I reveal like C1, it still reveals some information about A2. Right? Because like this value is now no longer just composed of the one value that has other values as well. So like for now, if I were to reveal C2 and C3, I would potentially be revealing some information about A1 and B1.
Yeah.
And that's like too dangerous. So what we do, at the end of this, we do this like kind of funny hack, which is we add like plus R1 minus R2 plus R2 minus R3 plus R3 minus R1. Okay, and like these are just random numbers less than P. And now, when you add these all up, they still equal C, right? But because the R's all cancelable. But now, because R3 and R1 are totally random, like because I've got C3 is all this stuff plus some random value, now you don't know anything anymore about A1 and B1. It's totally fully masked. Okay, cool. So we've got this like kind of long annoying computation for C. Okay, so now how does the reveal look? The reveal looks like slightly different. So previously, we revealed the second and third column, and then we calculated both of these values, and we learned nothing about the first column. There's a 1/3 chance that you could fool me. What we're going to do instead is with C2, C3, like now we're going to do the same process, but we're going to commit to all the values, including A1 and B1. And then again, we're going to choose two random values, let's say it's 2 and 3 again. And now we're going to reveal like both, like the entire column at once. Okay, so we're going to reveal all these values. Divider. Great. And like, I guess maybe for the sake of simplicity, let's just think about like the A, B's, and C's, like the ones that involve multiplication. Okay, so what exactly is the verification we're going to do here instead? Is we're going to verify, okay, like if you're going to reveal A2, B2, C2, and A3, B3, C3, like now what I'm going to do in this equation is I only have enough values to verify this middle C2 one, right? Because I now know A2, B2, A3, B2, A2, B3, and also in this commitment, they're also going to commit to, let me put H equals hash. They're going to do also reveal H of R1, H of R2, and H of R3. So they're also going to commit to these before I calculate my special secret hash on the right. And so here, like when I reveal A2, B2, C2, A2, B2, C2, A3, B2, C3, I'm also going to reveal R2 and R3 in step 3. So, okay, so how has step 3 changed now? It's like become slightly different. Like, okay, let me like rewrite these all to be ABC. ABC, ABC, ABC. Okay, and now this like HABC, and this is HABC. Great. Okay. So now what's going to happen here is I'm not like it's no longer the simple addition thing. Now I'm only going to verify our middle constraint here. So I'm just going to do this calculation over here. Because they're going to reveal to me those columns and also like R2 and R3 and R1.
So then are you regenerating the A, B, C, D, E every single time? Because like if you do this,
correct.
Then
yeah, so when I said earlier, like, yeah, we do this process 100 times, like each of the 100 times, they're going to start from scratch, regenerate all the random values A1, B2, A1, A2, B1, B2, and then compute A3, B3, and then compute all the C's, compute random generated D's, compute all the E's. And we're going to do that again and again because if the random number is ever repeated, and also R1, R2, R3 change, if they ever repeated, I might be able to learn something about the original. Correct. So like now if you put it all together, like, okay, so like for just the multiplication, what have we done? Now the chance you can catch a cheating prover is no longer like 2/3 of the time you're going to catch them. Now only 1/3 of the time you're going to catch them because you can't verify C3 anymore. So you might have goofed something in C3. You're only ever verifying one kind of column now. So your chance goes from like whatever, like 1/3 cheating to 2/3 of the time they can cheat. And so now like, okay, so 2/3 can cheat. So now like in your whole computation, you have to do this a lot more. Right? So how many times do you do this computation? Imagine you want to get like a security parameter of like 1/2 to the 256. Then now you have to do this.
They still need they need to get some in A and some in B. Are you saying collectively the number of terms there is still... So
like the interesting thing to note here is like C2 only involves terms from columns 2 and 3.
Yeah.
C3 only involves terms from columns 3 and 1. C1 only involves terms from columns 1 and 2. And so with only 2 columns, I can still compute at least one of these values.
Yeah. Wait, oh, I see. You can only...
Right, because I don't have A1 and B1, so I can't verify C3.
No, I got that. Sorry, can you remind me what's the thing at the very end that you end up showing? It's that you calculate C2 exactly and then it matches?
Correct, yeah. So what the verifier do is calculate C2 exactly and learn nothing about the original values.
Yeah, but they still would need to have some... Oh, I see, because they could just have C2, but no, they show me everything in column 2 and 3, right?
Yes, yeah.
So they need to have things that are accurate in both 2 and 3 for me to get C2 correct.
Correct.
So then it's not a 1.
Well, but the thing is, like, they could have tested it correctly, right? So in this verification, the only things, like, because now I'm only checking column 2, the only values I'm checking in this column are like A3.
That's what I was asking.
And B3.
Okay, so
right, but I'm never actually checking anything about C3. Right, so for instance, I could still fudge the value of C3, and our verifier will have no way of knowing. Yeah. It's a good question, though. Okay. Do you have any further questions?
It looks nice.
Yeah, so this is like very nice and simple. Okay, so now if there's a 2/3 chance we cheat, we can do this like 100 times or something. And now like the chance we cheated all those times is like, the chance okay, so the 2/3 chance we cheat and a 1/3 chance we catch them. So if I do it 100 times, then they have to not be caught 100 times, right? So this looks something like, is this correct? 1/1 minus 1/3 chance I catch them. So, sorry, so it's 1 minus 2/3 of the 100. Yeah. Because they get away scot-free 2/3 of the time, and they would have to get away scot-free 100 times to fool me. If it is 100 times, there's a chance that they cheated me, which is quite low.
Okay.
Cool. So now, like what I've done is I've showed you the zero-knowledge protocol, which I can combine any number of addition and multiplication. You can keep extending this chain forever. I've revealed random values in this computation. I can also reveal like B if I so wanted to, but I don't necessarily need to. And then, as long as I've revealed at least one of these values, you can verify the ground truth of one of the values in this computation, and the rest of them will kind of follow through this like verification that we do.
Repeat the last closing statement that you can...
So the last closing statement is, now to construct a general zero-knowledge proof, like I can define which of my values are public and private, right? So in this case, the square values are public, so let's say like B and E are now public. Like if I want to make more values public, I just reveal all 3 of the values. And now you can construct the original value by just adding them up. And so now I can define an arbitrarily long computation of additions and multiplications, make arbitrary ones public, and prove to you that whole computation is valid by, again, like revealing 2 entire columns of this whole computation, doing the relevant addition and multiplication verifications, and then proving that it corresponds to the hash that got sent on step 1. And this is like basically the entire protocol. And then you can implement this yourself in Python in probably 100 lines. And it would just like, in fact, work. Yeah.
Cool.
Yep.
And then as you increase the number of terms and the size of the polynomial, then
So
the
you'll
likelihood,
notice.
yeah.
Oh, go ahead.
I was gonna ask like the number of verifications that you need to do to have conviction. How does that change?
Yeah, so it's proportional, right? Because
Yeah.
what happened was that like here I have like two like kind of things I need to verify, and so now the verifier is doing like like whatever 2 work. But if there's like you can think of these as each of these as a constraint. So now if I have like 1,000 constraints, the verifier here needs to verify all 1,000 constraints. And so the verifier has to do a lot of work here. It's like proportional to the size of the original circuit. And like one of the interesting things that Sora did during the residency was like, oh, it turns out that like you're doing a shit ton of hashes. Like in just this example, I have like something like 12 hashes, and then I'm gonna do that 100 times. It's like 1,200 hashes, which is like actually a lot of hashes. And like at that point, the hash computation starts being like a time bottleneck. Like it actually becomes extremely time intensive to do all those hashes. And so one of the things you can do is instead of doing all of these hashes, you can replace them by this thing called a random linear combination. And that lets you do a lot of these hashes way faster because it's only one multiplication instead of each one being an independent hash computation. And so that was like the kind of innovation in the residency where this process became like something like 100 times faster by doing that. Between 10 and 100, like basically order of magnitude faster. Which is pretty dope. Yeah. So maybe my question to you is like, do you think you've understood this enough that you could like go home and implement this in Python? Or like, is there any part of this that's still like fuzzy?
I think I'm just confused about applications or like motivation. Yeah, like what I think the part when you're like when you expand it, like you have like 1,000 constraints or whatever, like what those would be for.
Yeah, so like, okay, so like, it's a good question. Like, this addition multiplication one is not super well motivated, right? But like, you can imagine something where like, the thing you actually prove here is you construct, say, a hash function or a signature verification function out of these addition and multiplications. And now what I can show to you is like, for instance, Laurent's application, which proves to you that like proof of passport is given a government signature on the NFC chip of my passport, like I verify that signature and those hashes within ZK by defining this sequence addition and multiplication that verify those values. And I only reveal, like, say, like, the country I'm from, or whatever. This is the ZKBoo verification I explained to you. And
What?
And I only reveal, like, say, like, the country or whatever. Like, and now what I've done is I've done this, like, entire long sequence of verification and only revealed one specific value. So I can prove to you I'm a unique USA citizen, but I don't reveal which one I am. Or, like, for emails, you can do a similar thing, where you have, like, again, this like whole long sequence where I verify the DKIM signature, and I output, say, the public key that should have verified the signature, and like some value I want to reveal in the email, and I hide everything else. And now because I've constructed out addition and multiplication, it's like very easy for me to do this verification.
And so
and like still keep what I want to keep private.
Is the main like formula that then tend to be constructed using this is hash functions that is then used to do stuff?
But like, the really interesting thing here is like, okay, so like this specific A times B equals C is interesting because now you know the prime factorization of a number, but that alone is like not like that compelling. Okay, cool, you know the prime factorization of a number, so what? But the so what here is that by combining like 1,000 or 10,000 of these, you can now construct a whole hash function, like the SHA-56 function or whatever. And like, because you can break down any value of these like Turing, any combination of these like Turing complete gates basically, or 2 gates. And now like the hash function is really interesting is kind of a one-way function, right? Like the end of a hash function is like some random value, and you never knew the value that came in, but I can prove to you I knew the pre-image of that hash. And something with signature, I can prove to you I knew a signature that verified some public key, but I'm not going to reveal to you the signature. And like these only become interesting when you compose enough of these to construct one of these like bigger like cryptographic primitives.
Okay, so in the example that they're doing with age at the beginning, is that first one would just be constructions of the A times B plus
exactly.
B,
So like,
and that's the hash and
precisely. So like you might imagine that like you do this whole passport check and you add these constraints for the range checks. Like you also have like x minus 18, whatever, is something, it's some variable, x minus 19 is some variable. You multiply them 2 at a time until you get this whole value, and now you've proved some value between 18 and 200, but you don't know what it is. And then you have the verification, like I proved it's between 18 and 200, and the US government signed that value. And so I can prove to you that I'm a citizen between these ages.
Wait, how do you get the U.S. government sign the value once I have the number? Like I can have an age and then do this whole thing,
Yeah.
but how do you connect that to?
So because what the US government has done is they've done something like they've said like, you know, sign of like hash of like X and like some other stuff and like USA and some other things, and signed with like the secret key of the USA. Like, kind of overlaps a bit, but like basically what you can say is like
Oh, Adil and Alicia learned ZK.
like so the idea that like the government has constructed a signature inside every passport of like the hash of all these values and like signed by some secret key.
Okay.
So what I can do now is I can prove this whole hash and do the hash computation, but I only reveal this X value. And then I reveal the public key that verified this signature.
So who's doing the verifying?
So the prover is going to do the verify.
Oh, like in an application.
In an application, the user is going to scan their passport, do that verification locally, construct the ZK proof locally, and then ship it off to the verifier and be like, look, I am in fact a citizen of that many years.
But they're shipping the hashes
Right.
and like
So-
the E.
So like
and the-
what I've shown here is this interactive protocol in which they ship like all these values, the verifier responds, they respond,
Yeah.
go back and forth.
Okay.
There's a way to make this non-interactive. You have the Fiat-Shamir trick in which you like basically this like secret randomness generating value that verifier is doing gets replaced by like some sequence of hash functions that the prover cannot like reverse engineer ahead of time.
Wait, but then they have it on their own device?
Like, yeah. So concretely, like, how would you do this? I'm trying to think, like, what is like, how exactly would you construct this hash?
I think in Fiat-Shamir you have to hash the whole history of the thing so that you can't like change it at one point.
Yeah.
But I also would not know how to explain why you can just brute force and try multiple like parameters at the beginning. Is it because there's like a deterministic way of generating them and so you can only check one?
Like, I think it has to do with, first you hash only the public inputs, you only hash like E and B, and then I compute some stuff off of that will never change, no matter what happens in the proof. And then you hash all the rest of the values, and then I compute some other hash that changes for those values, and the way I compose them is like some weird mechanism. I'm trying to think like how exactly you do this, because you have some hashes that don't change, like the public outputs, you have some that do, which are like all the other values.
Okay.
Yeah, it's a good question. I don't know why this is non-interactively secure, but anyway, at least you know it's interactively secure,
Yeah.
which is kind of good enough.
Stuff you were saying about non-interactive, like I don't know, it still seems gameable. It just
Yeah,
like it
so-
seems like a time thing.
Yeah,
that would
there's.
be hard.
I remember there being some argument of how they did the Fiat-Shamir to make it non-interactive, but I don't remember what exactly it was. And like an interactive ZK proof is like basically good enough in this scenario. And the trust is a way to make it non-interactive. I don't know what it is.
Yeah, because the security of Fiat-Shamir is not even something that you can attack via brute force.
Yeah. But like the prover might be able to like, what he's saying is like, imagine the prover knows multiple satisfying witnesses or something. Like
Yeah.
even if you hash like A, B, C, D, and E, like that still wouldn't work. But maybe you have a couple of different witnesses and you try all of them and you say, oh, one of these will work.
Yeah.
Like there has to be some way of doing this in which the prover like isn't able to try this multiple times until it just happens to work and it's
Yeah.
not to the verifier. Anyways.
Or maybe you just want to specify your circuit so that there's only one possibility of valid witness for the person.
Yeah, so then like theoretically but you can't necessarily guarantee there's only one witness, right?
Do what?
Like you can't guarantee there's only one possible witness.
Well, like in most applications.
Potentially, maybe, yeah. But anyways, the cool thing is that like usually it takes like years to understand ZK proofs, and like now I think you can probably program your own in like straight up like 3 hours, which is like pretty nuts. This is like by far the simplest thing.
Is that a blog post explaining this?
No, but we really should. Like geometry has a blog post,
Yeah.
but geometry is extremely technical.
Yeah, it's
There's
super
nothing
serious.
of this simplicity, and I really want to write it.
I saw it and was like, no,
Like I don't think like
it's Ying Tong did it.
yeah, Ying Tong and all wrote that. And it's way better than the paper. Like it's already a step above the paper. Where like there's no way a non-cryptographer can understand the paper, but maybe if they grind really hard to get the blog post. But I think literally anybody who knows like middle school math can understand this.
Yeah.
But like I just haven't had time to write the blog post yet. But we should really do it. Yeah.
Take the transcript.
That's exactly what I'm thinking. I hit the transcript, take a picture of the board, I'm like, Claude, figure it out. Like,
Yeah.
yeah.
Cool. Cool.
Nice. Now you know ZK. Now if somebody asks you, how does ZK proof work? You can explain it. Great.
Thanks.
Yeah, of course.